is now under that subset relationship, saying this. And this part, under that subset relationship, is telling me this.
So if I may say, right, we have two conditions now. If A equals to B means 1, if both the sets have the same element, and if A is an element of B and B is an element of A.
Firstly, having same elements is rephrased in this way. Okay? Now, this statement, X belongs to A, implies X belongs to B, has been given another form by saying A is a subset of B. Oops, what happened? One minute. Yeah. So this has been given the form A is a subset of B. And this statement has been given a form B is a subset of A. Okay? So there are no more two conditions. I'm saying it's the same thing.
Okay.
Alright? So computationally, it seems simple to look like this, but it is not at all anything new. It was already there. Yeah, except that I have said it in terms of nice relation. Okay? Now, over here, let me emphasize, as an example, here is a nice example. The empty set is a subset of every set. How do I prove this? Okay? So how do I prove this? So what do I have to show? So I have to show if I take an element from X, then it means right? Right? But what was this empty set? Empty set is the collection of all those elements so that is not equal to itself. Right? So that means how the hell do I prove this? Take an element. This is where our basic logic comes to our rescue. So that's why I am doing this also. So this is a basic fact of our logic. And what is this? Well, firstly, as I said, you can make statements. Okay? So X belongs to A is a statement. X equal to Y is another statement. Okay? We have already built many other statements. So if alpha was a statement, so X belongs to A, beta was a statement, X belongs to B, then we have made this statement alpha and beta, which means X belongs to A and X belongs to B. That's the third statement. Right? Here's the fourth statement. X belongs to A or X belongs to B. Okay? Similarly, X belongs to A implies X belongs to B is yet another statement. Now, a statement can either be true or false. Okay? Good. Now, how does a statement which is of the form, say, alpha is a statement and beta is a statement, Now, when does this statement alpha or beta is true? Well, I know. Either alpha or beta is true. This is true, right? So this is true if and only if either alpha or beta is true. Now, how is this statement? Alpha and beta. When is this true?
Alpha
Both is true. Okay? If and only if both now, yes.
So the first statement implies that at least one should be true. So even if both of them are true, it's not fine.
Yes, it's still fine. It can be false when both of them are false. It's quite natural, right?
But
Quite.
if at least one.
Yes, if at least once. Now, about this one, this one is a notorious one. There are many ways of making this seem true, but the best is this. Let me tell you, this is a notorious one. And the best is by stipulating. Why? The story is very, very long. Since it is notorious, well, people had ways to explain this. But again, the question started by questioning that notoriety, which I'm going to say. Okay? And several different kinds of logics emerged. So it is not, the logic that we use is not the one and only one logic. There can be several other kinds of logic in which you can develop mathematics as you develop here. So it's actually a big project. It goes on. There are several people who work in that and so on. But for this course, we are going to believe this logic of ours. Okay? So let me stipulate the truth table for this. Okay? So what about alpha? Alpha and beta. Now I'm writing the truth values T for true and F for false. So alpha beta can have all these possible values. Okay? And this one's huh? Sorry. Yes. Thank you. Here? So the statement alpha implies beta can be false in the only case in this statement alpha is usually said to be the hypothesis. Okay? Beta is said to be the consequent.
Excuse me,
following. Yes?
Can you please explain the table again, the truth table? How do you get to the...
It is not about an explanation of the truth table. This is the truth table in this logic.
Okay, but the law of logic, how do you get the true, false, true, how?
See, the first two columns is quite simple, right? Alpha and beta can have only these four values, the pair, because alpha can be either true or false, beta can be either true or false, so the pair will have only these four values. Okay?
Okay.
Now I'm telling you what would be, in each one of these cases, what would be the truth value for the statement alpha implies beta.
Okay.
So when both, so let me have some names. In the statement alpha implies beta, the statement alpha is called the hypothesis, beta is called the consequent, and the statement is called the implication statement. Okay?
Okay.
So alpha implies beta is the implication statement. Now, so what does this say? When both the hypothesis and the consequent are true, then the implication statement is true.
Okay.
When the hypothesis is true but the consequent is false, the implication is false. Okay? Up to these two things are quite acceptable. Alright? The real notorious part comes in the next two. It says, if the hypothesis is false, no matter what the consequent is, true or false, the implication is always true.
Okay.
So as if it is trying to say that from a false hypothesis, you can conclude anything. Okay? So I'm not saying that I'm concluding beta, I'm saying the implication of alpha implies beta is true. Okay? So these two are the notorious ones. And these two are called vacuous implication. These two are called vacuous implication. V-A-C-U-O-U-S. Vacuous. Vacuous means from nothing. So, right? Vacuous implication. So whenever we are going to use this, we will say by vacuous implication, or the implication vacuously follows. Okay? So, let's see how am I going to use this. Now,
Sorry,
this
sir.
one. Yes.
Sorry, sir. So in this sense, when you talk about the hypothesis, are you just talking about any hypothetical statement that I make in mathematically when you talk about hypothesis and the consequent? So what would be a hypothesis in terms of an example? What would be a consequent in terms of an example, in terms of a mathematical statement here?
Correct. That's where I'm coming back again.
Okay.
So I was trying to say that the empty set is a subset of every set. Now that means I have to show that if X belongs to the empty set, then X belongs to A. So this implication statement must be shown. This one must be proved by definition of subset. Now X belongs to empty set. Remember, the empty set was defined as the set of all those elements which does not equal itself. So, this statement is therefore same as showing this implication statement, the second one. Okay. Now let's look into this implication statement. This one is false. So, this is the hypothesis which is false.
Excuse me, sir. Sorry to take you back. How do we know that that is a hypothesis statement?
Anything which comes to the left of that implication sign is the hypothesis.
Okay.
Yeah? And right of the implication sign is the consequence. Okay? So, X is not equal to X. That's a false statement. Okay? So therefore, the hypothesis is false, and by vacuous implication, this implication statement is true. I didn't say anything. I say, since the hypothesis is false, the implication statement is true. Okay? So this statement is true. Therefore, the first statement in this first line, this is true. And therefore, by my definition, this is true. So, empty set is a subset of any set is just an explanation of the use of vacuous implication.
Sir?
Yes.
Sorry, again. Look, from the example here, you have that theta. That's an empty set, isn't it?
Please don't call it theta. It is not theta. We call it the empty set. It is also not phi. It looks like phi.
Okay.
It's called the empty set. Yes.
So
Yes?
this is the example is saying the empty set is a subset of A.
Of any set. A means, I meant by A, any set A.
Any set A. Okay. Okay.
Any set.
So how do you? Yeah.
Yes.
So then you move to say, then you come and say to show the two next statements that you have, X element of an empty set implies X element of A. I get it. Are those the statements that we are, say, when I look at that example, is it something that I have to start writing when let me say I'm trying to prove the statement? Is it something that is a statement? Okay.
Yes. Yes. You see, if I have to prove that the empty set is a subset of A, by the definition given on the first line, I have to show that if X is a member of the empty set, then X is a member of A.
Okay. Okay.
Right?
Okay. Yeah.
Yeah. Is it clear now?
And then the second statement, which is X not equals to X.
Yes.
Yeah. You're saying that statement is false, but isn't that because when we look here, even isn't that the case for an empty set?
Yes. So that's what I say. Remember, I defined the empty set where it is 2 pages back. Yeah. See, from special set number 1. Empty set is defined to be the set of all those x's such that x is not equal to x.
Okay. Yes.
So that's what I have written. So by saying the first line x belongs to the empty set, I mean that element satisfies its defining property, and hence x is not equal to x.
But why is it false? Why is it false? Is it not supposed to be true?
Wait. Can you find an element, anything in this world, which is not equal to itself?
No.
That's right.
Okay.
Yeah. Clear?
Yeah. So in this case, which means the first variable, which is the x on the right hand side, represents the alpha.
Yes. X not equal to x. This represents this alpha.
Oh, and then the second x of the variable.
This one. This x belongs to A represents this beta.
Oh, this beta.
Yeah? Okay? So alpha is false. I don't need to see whatever beta is. The implication statement is true. Yes. So I have proved the truth of this implication statement, which therefore means that. Okay? So that's the whole crux. Yeah. Any questions? Okay. Let's carry on. Now about this relation. This is very much like our numbers. It's a kind of a comparison. See, what is it? What do we mean by the notion of comparison? Well, if I'm going to compare the objects x, y, z, then I know x, any object is equal to itself, so it's a particular case of it's comparable with itself, right? If x is smaller than y is smaller than z, then x should be smaller than z, right? And if x is smaller than y and y is smaller than x, then no way, they must be same. Okay, so this is the very natural notion about comparison that we have, and that's exactly what we see. If A is a subset of B, and B is a subset of C, this automatically implies okay? Quite trivial. If you run down you take any element from A, it is in B, and therefore this one says it is in C. Yeah. Okay? So obviously this is true. Now this one is also true. Every element of A is in A. A is a subset of A. So these are the things that we showed, and this we saw is the other way of looking into equality also. Okay, so everything falls back. Okay, and we have also shown this. All right. So these are the few properties of the subset. We will define some operations now. Given this statement for OR, so we define for any two sets A and B, we define this set called the union of A and B. This is called the union. This is called the intersection. This is called the complement. Okay? Now, so if you try and look into some diagrams, if this is A, this is B, A union B is the whole. This common part, this is A intersection B. The part away from A, okay? Okay, the part away from A, which includes B also, that's A complement. Then A minus B, it is called the relative complement. It is X belongs to A and X doesn't belong to B, which is therefore nothing else but this. Okay, so this part is your B minus A, and we have something called the symmetric difference, which is the join of these two. It's called the difference. Okay? Or the relative complement. Relative complement of B with respect to A. Okay? So that's the names. And the first problem in your self-assessment asks you to prove some equations for these operations. For instance, A union B is same as B union A. So, for instance, how do you show that? X belongs to A union B if and only if X belongs to A or X belongs to B. But this is the same thing as saying X belongs to B or X belongs to A, which is then by definition the same as X belongs to B union A. Okay? So A union B is equal to B union A. Okay? So that's how you show these things. Yes?
So the last line, how would you say it out? Is it A?
Which one?
The last line. How do you say? How do you pronounce it?
Oh, we say symmetric difference.
B.
A, symmetric difference. Okay. All right. Now,
Excuse me, sir.
yes.
Can you please repeat you mentioned on the assessment when you're saying prove the following equations, you were giving how we prove them. Can you please repeat that again?
Yeah. So let's see. So suppose I have to show right? Then how do I go about this? Well, I start off with an X coming from A union B. This means by definition that I have given X belongs to A or X belongs to B. This means by definition, therefore, by plain this sentence is same as saying X belongs to B or X belongs to A. And this last sentence is same as saying X belongs to B or A. So what I have shown, if I take an X from A union B, it is in B union A, as well as if I take an X from B union A, it is from A union B. So this says, hence,
Okay.
That's the complete proof. Clear? All right. Now, the next one is a little bit. So we want. I said everything is a set. Okay. So the notion of equality obviously tells us that this set is same as this set. Yeah?
Yeah.
But, so this is often called the unordered pair. Why unordered? Because it doesn't, so in a set, as we have seen, writing an element 20 times doesn't matter. Similarly, there is writing the set of first three natural numbers as 1, 2, 3, or 2, 1, 3, or 3, 2, 1 doesn't matter. There is no order inside the set. It is just a bag. It is just a bag, it is just a collection. There is no other notion in it. There's only one notion, something is there or is not there. Yes.
So what happens that in the first, the left hand side, it has maybe 2 sets, and the other one has 3 sets, which means...
Good. So now, obviously, you know.
X and Y.
Yes?
So does it mean they're not going to be equal due to...
Obviously, you know this is obviously equal to this.
Oh, yes.
Yeah? So, but you know that this is not if.
Sorry. I want to compare this with the Q in I minus W. Sorry. Are you looking here? Sorry? Are you looking here?
What's this?
Oh,
Hello?
Thanks. Do you perhaps know where I can get this class? Because I feel like I'm in the wrong class.
I think once enter you can go and check on that screen.
Okay. So, right? So now I'm going to give you a third one. In fact, it's a little more involved. I gave this as an assignment, but it is level 2. Okay? And if you can do it, you actually got hold of this membership business pretty well. If and only if. And strange, right? So it is a little bit of a manipulation. It's a little bit of a manipulation that I did with those, and it is a little bit involved. You have to go through few of the cases that come up with this equality and so on. So I'm not doing this, but you try it yourself. And then if you cannot, then we can speak. Okay? Now, so this is now something strange. Let me put a symbol.
Okay, so here are we supposed to prove that two sets are equal?
Yes.
Okay.
Yes. The statement says therefore, these two sets are equal if and only if X is equal to P and Y is equal to Q. Okay? Now let me just introduce a symbol. I'm going to say this. As this set. Okay? And let's see what this statement therefore gives us. It therefore tells that xy is equal to pq if and only if x is equal to p and y is equal to q. So it is exactly what I was wanting of an ordered pair. Okay? So when I want the extra notion of an ordered pair, I would use this particular set, xy written in this way. So this is called the ordered pair of x and y. X is called the first component or the first coordinate, and y is called the second coordinate. Okay? And xy is the third set, which is called the ordered pair of xy, x and y, the bracket xy. Yeah? So this is how we shall bring in ordered pairs, and why do I bring in? We will very soon come to see. We have, therefore, this set consists of all ordered pairs of x and y, so that x belongs to A and y belongs to B. This is called the Cartesian product of A and B. Okay? So, for instance, you have your R cross R or R2, the plane, given as a Cartesian product of A, of real numbers. Okay? So, that's something, well, we will, okay, that will come. So now, this set will be with this kind of set A cross B. We will see, we will be using it again and again. And we will also like to have ordered triples. Like x, y, z. Then ordered quadruples. Like x, y, z, t. And in general, ordered n-tuples. How do we do this? Well, it's just a little bit of an extension. So we put this as
Tuple implies order.
yes. Okay. So that's how we define this set. But remember now, what does this say? I'll work it out for triples. So now let me see. X, Y, Z is equal to P, Q, and R. This is the same thing as saying, by my definition, X, Y, Z. So this pair, which consists of the first coordinate being X and the second coordinate being the pair Y, Z, is equal to this pair. So it's the same thing as saying, by my property of pairs now, that X is equal to P and the pair YZ is equal to the pair QR. But then this tells me X is equal to P, and from this fact about two pairs, Y is equal to Q and Z is equal to R, which gives me exactly what I needed.
So basically, just have to break it down step by step.
Yes.
So you have to group them.
Yes. Yes. Okay? So now you know how to define. So if you define your ordered triples like this, your ordered
Sorry, sir.
quadruples. Yes.
So just to check something here. So for instance, let me just start with the x, y, z equals to PQR. Then you said according to the definition. Now, is this according to a universal property definition, or is it because of the definition you stated at the top there?
Yes, it is. Yes. I'm saying I will define. So this is my definition.
Okay.
Of an ordered triple. So
okay.
The triplet x, y, z inside brackets is defined in terms of the ordered pair. And what is it? The first coordinate is x, and the second coordinate is the pair yz.
Okay, so this definition, is it definition that you are giving, or is it based on a certain property, or like your commutative properties?
No. The whole intention, as I say, see, my whole intention of ordered pair was to bring in a way to say that I have a set in which x is the first thing and y is the second thing. Okay? Now, curly bracket xy doesn't provide it, so that this strange formulation over here gave me this desired result, which is actually written down in this line.
Okay.
So, well, now having done with ordered pairs, I'm just extending that same method to triplets, quadruplets, pentets, and so on. In general intervals. Yeah? So how do I do it? What should be an ordered triple? So I define it as a pair. Remember, pair is already a set. So I define it as a pair whose first coordinate is x and second coordinate is the pair yz.
Okay.
So I go on similarly. So what would be the quadruple? So I define this as, in terms of the previous one, right? So you know how to define your n tuples.